Hello everyone. So the project topic for the chaos team is Tage and Tagel branch predictors for simulation in ChamSim. So Tage is not just made of tags, but it is much more. In computer architecture, Tage refers to the Tage branch predictor, which stands for tag geometric length predictor. It is derived from a combination of PPM like tag based branch predictor and also uses geometric history length predictor, which is similar to that of OGHL predictor. And the tag components make use of lengths of global histories which form an approximate geometric series, which can be given by the formula Li equals int of alpha raised to I minus 1 into L1 plus 0.5, where Li is the length of the ith component of GHR. When did Tage become so popular? To discuss brilliant ideas about branch prediction, many championships take place, and Tage got its recognition in one such event. One such event was Championship of Branch Prediction 2016, where multiple submissions of TageL, which is stage plus a loop based component, were witnessed, and Tage had given very good results for it. What is Tage predictor made of from a 10K feet view? Let's see. Tage relies on several predictor tables, which are T0 to Tm, which can be indexed through independent functions of global and path history as well as branch address, which is IP. The base predictor used is the bimodal predictor, which is 2-bit predictor. Now let's see what does each TAT component or table contain. An entry in a TAT component consists of a signed counter CTR, a tag, and an unsigned useful counter U. So in the study and the research paper, U is an unsigned 2-bit counter and the prediction counter CTR is a 3-bit counter. So here is the structure of Tage. So we can see various components. T0 is the base bimodal predictor and T1 to T4 are other TAT components. We can index into each of the tables using IP and global path history and the path history, and each table makes use of GHR of different lengths which form a geometric series. Now essentially we take the matching component, that is one whose tag matches and which has the longest geometric branch history, and we make use of that to make the prediction. Why is stage branch predictor so relevant, and is it really a state of art predictor? So in Tage, entry tagging and better entry selection reduces risk of unnecessary high warm-up times. So Tage basically uses a mixture of very old branch histories and very recent branch histories, and making use of them it is able to increase the accuracy and overall performance.
The implemented Tage predictor features 12 Tage components and a base primary predictor. In each entry of the Tage predictor, there is a 3-bit predictor counter, takes of different widths, and 2-bit useful counter. The history length for each table is different and is based on geometric series. Similarly, for the LTH predictor, it contains an additional loop predictor component where each entry consists of iteration counts of 14 bits, tags of 14 bits, confidence counters of 2 bits, and an age counter of 8 bits. The result that we obtain from the LTAs and TAs predictors is compared with the bimodal predictor and an hash perceptron branch predictor. As observed in the bar chart, TH and LTH shows an improvement in accuracy from the basic bimodal predictor and shows similar results with respect to the hash perceptron. We also observed decrement in MPKI values for the TAGE and LTAGE predictor with respect to the bimodular predictor, while the values are similar to the hash perceptron. TAGE predictors are optimized to achieve ultimate accuracy for a given fixed storage. It inherits the use of geometric history length series from the OGHL predictor, but is more storage effective. The LTS predictor can be directly adapted to hardware implementation as a multi-cycle overriding predictor, making a first single cycle predictor and achieves very high accuracy.